Mr. Pramod Kumar, Senior Vice President, XDLINX Lab, and Mr. Ashesh Mishra, Head of Client Solution, Aalyria Technologies. Can we have a huge round of applause for all our panelists? Thank you so much.
Thank you to the MC, and thank you for coming back for our session. As today we are still missing the chairman, I got promoted to be the co-chair, and I would then take the pleasure to start to give you a short introduction. What do we mean, if we talk about mesh network? What is it about? And therefore, I will go quickly here. Okay. My name, Alexander Jeuck. I'm working for Novaspace as a senior advisor to them. My experience is in the space industry, working for more than 20 years with SES, with Airbus, ST Engineering. And of course, the idea of having mesh capabilities is making the satellite systems smarter, more capable, more useful in certain ways, because we cannot keep all the work, the processing work, the coordination work of huge constellation or even smaller constellations on the ground. And therefore, I want to give you a few hints, So mesh networks. In space mesh networks, satellites play the role of network nodes and can route data or traffic. That's important to understand. So we will not always go to the ground. We will go from satellite to satellite. In classical observation system, merely LEO constellations, the data transmissions to the ground is a real challenge, as the satellites are in visibility of the ground stations during only a few minutes every orbit around Earth. The use of mesh networks allows to create permanent connectivity between the observation satellite and the ground, at least for the satellite commanding. This reduces drastically the latency between the command and the procurement, acquisition and delivery of the image, which is key for some services, particularly for defense or military services. But of course, this is not only for Earth observation important, also more and more it gets important to shift data quickly, even quicker than on Earth, over satellite links between satellites. Classical space telecom systems are using mostly star topology networks due to their simplicity and compatibility with analog hardware. Few geosatellites can create hybrid star and mesh networks, as it requires complex switching systems only affordable to digital payloads. Digital payloads is something coming up the last few years because they are, of course, more complex, more costly, but this is what we see more and more in the future. Before it was bent pipes, important to understand. This type of mesh network are mostly used for governmental applications so far to create ad hoc local base stations in theater of operation. The introduction of massive LEO constellation in the landscape brings new technology needs and opportunities. Keeping a star topology approach requires a huge ground segment that only few actors can afford. Using space mesh networks is an efficient way to reduce the ground segment footprint. It allows to create secure communications without being in the field of view of gateway and without coming back to the ground. It can also provide low latency communication by the geometry of the constellations and the possibility to create direct paths between 2 points. Very important. In principle, we would not, we can go rooftop to rooftop. Gateways are, in principle, not needed. There are operators who praise that they are providing gateway-less services, which is then a very private service. Okay? Then examples of mesh networks in Earth observation systems. is, for example, several companies are using the mesh network capabilities as a leverage to provide more frequent access to classical observation satellites. This access can be more direct access to the observation data via the dedicated data relay system. Data relay systems are also a kind of mesh. In this case, for instance, of SpaceLink and Warpspace, they are the global coverage of LEO and MEO constellations, allows to send back the data directly to the wanted ground center. This can also be an access to the telecommand system of the observation satellite to reprogram it without being visible of the ground station. So there had been a few attempts and a few constellations looking into that. For example, there was a company called SpaceLink, which unfortunately, I have to say, disappeared, at least for the moment. Then Capella, they tried to do something like that. Warpspace, but also, for example, a well-known system building a relay satellite is the EDRS system, collecting in principle data and shifting it to another satellite and then brings it to the ground. Telecom mesh networks, for example, are Lightspeed, yeah, Starlink, at least version 2, Kuiper Amazon, Boeing had some constellation in mind, at least. Yeah, I'm not sure if they will go for that, which was a V-band filing. The Inmarsat orchestra is in principle also the idea of having a mesh network. Iridium Next and previous project was, you maybe heard about the space router. This was the Cisco Iris router. People called it router in the sky. Telecom network examples are there, and this is especially working then on the LEO constellation mesh networks. Large LEO constellation projects with hundreds to thousands of satellites have been enabled by key technology improvement on payload, on the platform. Platform means solar array, battery, propulsion. Payload means the high frequency solid state amplifier, high capacity ADC and DAC. And then, of course, on the launcher, which makes it possible to bring all that to the space. The constellations provide global communication over the Earth. However, without inter-satellite links, the communication are possible for satellites only in the visibility of ground stations again. And this requires a very dense terrestrial infrastructure. This infrastructure is either provided today by the operator themselves with many gateway stations or on the Earth observation systems. We're having so-called ground station as a service operators. They are taking that role. But let's say in the northern hemisphere or in the Arctic, when you come to if you have a polar orbit, there's not that many stations. So these stations are heavily used, heavily utilized. So for example, if you could shift that traffic from one satellite to another and go then again to a ground station or ground station network that is more accessible and more affordable, that can change the dynamic of a business case, for example. Of course, it also takes some time to go from satellite to satellite with a laser link. Now on the hybrid networks, which we are building between LEO, MEO in a kind of geo-hybrid network, this is something which is discussed also a lot with startup companies, because the startup companies, they have to decide, where do I get my telemetry channel? Where do I get my data channel? Can I transmit from my satellite via satellite to a network? So for example, one solution I know is using a kind of Inmarsat system connecting to Inmarsat and then going down from Inmarsat. It's also a kind of mesh. These mesh systems, however, are particularly complex from end-to-end network point of view, as they need global resources, coordination, and optimization. Indeed, space routers are less autonomous, flexible, and capacitive than their ground counterparts. Because you have to see that, of course, if we are doing things in space, we're still having to overcome the problems like power. If we need processing power, that requires power. Processing power means heat. How do I get off the heat? So the complexity, of course, goes up. Then, one more word to the onboard processors. In large mesh networks, the use of regenerative processor is required to route the signals. Transparent switching, analog to digital, is quickly very limited in the number of hops that the data packet can reach. And further challenges is the intersatellite links bottleneck, we call it, yeah? Even if intersatellite links can be seen from a network point of view as simple Ethernet cable, yeah, their implementation in space is far more expensive for optical units. Thus few ISLs, which are already installed, typical 2 ISL for the interplane connectivity and 2 ISL for the adjacent plane connectivity, orbital plane, I mean, not the plane, yeah, connectivity are installed. Another limitation comes from the total achievable capacity per link. There we talk usually about rates from 10 gigabits for optical units, 800 megabits for RF units. So people trying to use, for example, V-band spectrum to have also communication between satellites, but preferably these days, people would like to have the intersatellite links on optical basis. All traffic from all linked satellites not in the range of a gateway must pass through the satellites that does have gateway coverage. This creates the bottleneck requiring very tight resource planning and allocation. So for example, the congestion effect is driven by two factors, mainly the number of ISL hops required to reach a ground station, and of course the capacity served by the adjacent satellites. Then the roaming aspect, that is another challenge. Roaming includes all handover aspects in critical topics in satellite constellation, as it is a must to be seamless for the user. Operating a IoT constellation where you not always need to be real time is of course a completely different story than to operate a broadband SLA where you need to have extremely high availability. And with that, I can maybe add the difficulty we see in the space mesh networks come from the dynamic of the overall topology. For LEO constellation, the user terminal of the gateway is a visibility of one satellite during few minutes. I repeat it again, but I think that is in principle the motivation because that's the bottleneck on the ground and also with the ground station, yeah. The topology in space mesh itself is static. That's important to understand. The satellites remain in the same position relative to each other in the plane and also in the adjacent planes. The quick evolving topology at system level is far more dynamic than ground networks. The space segment topology itself remains totally predictable. So depending on the level of onboard autonomy for the routing aspect, the ground needs to anticipate the future link and resources for upcoming communication. This is a rather complex task, and with that mentioning, I want to go back to my seat and hand over to Aalyria, and they have some nice presentation, I think, and you get more aware of the topic. Thank you.
Thanks, Alex, for that wonderful overview, and also for claiming that the presentation is going to be nice. Questionable at best. First question, is there a clicker? Oh, okay, that's fine. I have no memory of what slide is in what order, so we'll play it by the ear. I know we are coming close to lunchtime, so everyone's energy is going to be a little bit low, including mine. So let's keep this interactive. We are a small enough forum here so that we don't get distracted too much. So we talked about mesh networks. Let's talk for a couple of minutes about how you end up with a mesh network as a company. There are predominantly three ways that you do that. One is you are a commercial satellite capability provider. You ended up being successful in the market by some stroke of luck. And you got enough money that you started acquiring other companies. So once you start acquiring different companies, you end up with different satellites, at times in different orbits that have different capabilities. And you want to run the whole set of your resources as a single network. Of course, running them as a single network is more efficient. The other method, which we are starting to see a lot more now, especially in countries that have relatively sizable space defense budgets, is you have different agencies within your Department of Defense that have started launching their own satellite capabilities for one reason or the other, to maintain some degree of control or to maintain isolation and resilience. That works great during peacetime. During wartime, when you have adversaries jamming certain capabilities, you are at the risk of losing some of your space assets now with fairly sophisticated anti-satellite operations. The new trend is to develop this concept called hybrid space architectures. So if you go to the Defense Innovation Unit's website, you'll see HSA as a pretty important construct. It's nothing special. It's just a framework for integrating different satellite networks and having them be available to all units in tactically responsible timeframes. So you have one unit that is about to go into the operational field in 2 hours to respond to an incident. They typically don't have enough time to write a requisition order and wait for someone to provision manually the connectivity, the specific type of connectivity and the specific type of observation that that mission needs.
This one for the next slide and this for previous.
Perfect, thank you. Now, the third option that you end up with is you are a commercial operator or a government, and instead of scaling your own network to have diverse types of communications, you're now establishing partnerships either with your allies or with different companies to create an overall richer ecosystem of services that you can offer to your end consumer. We are starting to see this quite a bit. Viasat is now reselling Starlink services. Intelsat is reselling both OneWeb and Starlink services and so on. So you're an entity now that has a hybrid network which is more complicated in some ways than a single geo satellite. The problem that you end up with now, which did not exist a couple of days ago, was how do you overlay services on top of this hybrid network so that your network is operating efficiently and is also responsive in a at least somewhat autonomous manner. So what you see here is how SDN systems, software-defined networking systems, have been developed for the past 15, 20 years. This comes from the terrestrial networking world. So if any one of you is from telco, this will be very familiar to you. You start with a network graph of all of your nodes in the network. These are your routers, these are your cell towers, any microwave radio that you may have, and so on. You're going to create a graph that has the interconnectivity between all of them. And then as you start adding new user services, you're going to solve that graph repeatedly for creating the routes across your network, right? This works really, really efficiently. It takes relatively less amount of compute, relatively less amount of storage, because you are not in the business of predicting what that link's behavior is going to be in real time. It is typically a physical wire. Even in the case of radio, it rebalances to a nominal rate at which that radio is going to work. The nodes themselves don't move, they don't come in and out of existence unless there is someone physically cutting a fiber or someone is physically adding a new cell tower. So a static network topology allows you to iterate only on step 2 and 3. Once you start adding non-geostationary assets into your network, this stops becoming true. What's happening now is that all of these nodes are moving relative to each other, nearly continuously. Like Alex mentioned, for LEOs and certainly for MEOs that are in equatorial orbit, that motion is for the most part predictable, but it is still constant. What ends up changing in a much more dynamic fashion is what the quality of each one of those links is going to be. Because let's say I have a satellite right above my head right now, and let's assume I get 100 Mbps on a relatively cloudy day. Tomorrow, when that satellite is back at the same point, I'll get a different capacity from that link. Now, as these companies started evolving the SDN systems to control these more sophisticated networks, what they ended up doing was, you know where each satellite is going to be at any point in time relative to the user terminal. And you kind of know the capacity that you're going to get at the bottom of your arc, at the top of your arc, and at the end of the handoff. So why not calibrate this link capacity to the capacity that you think is going to be nominal, right? So it's a safe measure. You think you're going to be able to hit that capacity 99.5% of the time, which is typically the SLA if you're using enterprise grade capacity. Starlink, there doesn't exist an SLA for it. So that's a different concept in a lot of ways. So really, what you're doing is you're using a very inefficient graph to iterate over steps 2 and 3. So the types of dynamic behaviors that we see in that graph. One, it is time dynamic. Different assets are at different locations relative to each other. This becomes incredibly more complicated when you start adding aircrafts as user terminals, because they are going to move across satellite coverage regions. So your cell predictability becomes a lot less. It is also time dynamic in a way where if you're using high altitude platforms, then your quote unquote satellites, which are your HAPs, move in unpredictable ways. They may be available today, they may not be available 1 hour from now. And thirdly, there is a need, especially in Earth observation, to have contact times with ground stations based on specific requests that have been coming in for customers for imagery of a particular area. This is not possible to predict beforehand, and you need to have a system that can respond in real time, or near real time at least. The last one is dynamic intent, and this is, fortunately or unfortunately, this is a constraint that is coming from the modern state of warfare, where waiting around for manual intervention to enact your resiliency mechanisms is no longer viable. So we need machine-to-machine interfaces where if everything goes south, You still have the ability to procure and control third-party resources, whether they are commercial or they are from other branches of your army. And that's the federation system concept. How do you survive a very deliberate attack on your system, or how do you survive a very unexpected in scale, scope, and time natural disaster? So what we have tried to do to solve it at Aalyria is we fix the problem with step one. We don't assume that there is a fixed network graph. We recreate this network graph by calculating the candidate link capacity between any 2 points, overlaying on top of it constraints of weather, historical traffic patterns, expected services, regulatory constraints, geographic constraints, frequency constraints. And we do this in every one of our solving cycles. And when I say we do it in every one of our solving cycles, even for a very large network of thousands of satellites and hundreds of thousands of network nodes, we do this every few seconds. For a small enough network, so let's say you have 100 satellites and 20,000 user terminals, we do this every couple of hundred milliseconds. And that allows you to have very tight and accurate predictions on what the link quality is going to be for each one of those links right now. And that also allows us to predict into the future with relative accuracy that for the next 12 hours, we expect the behavior to change in a certain way. So when we create a route for a user service end to end, we do not make a prescription that that route doesn't change over a period of time. That route will change over a period of time because it needs to. It needs to for resiliency. It needs to for efficiency of the overall system. So just as an anecdote, what we have seen typically is an overall efficiency gain. If you look at yield as dollars per megahertz served, of fairly large double-digit percentages over the previous way the networks were run. So overall, what you need in the modern NGSO world with mesh networks is a system that can first emulate your network, create a digital twin of it so that you can figure out if you're designing in any inefficiencies before you build your satellites, before you build your ground station network. It helps you with planning of how much throughput you need to each ground station, where do you need to place certain nodes to have the right contact times. Once you've done the emulation and optimization, you use the same system to orchestrate the live production network. And the benefit of using the exact same system to orchestrate is that now that the system is live, your behavior is going to be the same as was predicted in your emulation time frame. And then lastly, you want to be able to coordinate your capacity, your spectrum, your frequencies, your services with third-party partners or allied agencies. And we do this by using an open source federation API, which if you go to our website, you can find documentation for all of our APIs. You're welcome to use it to build your own orchestration system. We've published it as open source a couple of years ago. And yeah, if there are any questions, I'd love to answer them after the next presentation. Thank you.
Thank you. Good afternoon to all the eminent speakers here and all the audience here. So I'm Pramod here from XDLINX Labs, Senior Vice President. So let me give a brief about our company and where we stand in this particular technology of building mesh networks in space and smart mesh networks when we say so. So we are a satellite as a service provider. We are small satellites ranging from 10 kg to 200 kg class of satellites. And coming to the mesh networks and other things which previous speakers have already mentioned. So conventionally, space communication had been point to point, and it was more of a geostationary satellites were used for communications, and it used to have a lot of ground segment and other things. When we talk about current generation, next generation mesh networks in space, it's exactly emulating what we are having on the ground terrestrial networks, what we have, where we have a lot of gateways, routers, and other things which we are used to in our internet world. So, bringing this into space, it has its own challenges, and also it has many advantages. One, it can be easily time to realize to or a remote place is very fast once you build the infrastructure. But having said that, having previous speakers has already mentioned, introduced the topic. So having this kind of a mesh network in space has other challenges, which there a couple of challenges which we need to address, and that is where XDLINX, as a company which we are trying to build, is one is in the position of the satellites have to be relatively in the same position. So you know very well in space when the satellite is in LEO orbit, especially they have a drag and they keep coming down, and then continuous orbit maintenance maneuverings have to be done so that the link is always established. So this is a major challenge uh, for which you need a lot of, or you don't rely on ground stations, and you don't want to do this as a ground station operation. This needs to be done by the satellites on board. Onboard intelligence has to be added, and also as Ashish has mentioned, so dynamic routing, when you want to do that, so you need a lot of processing and intelligence on board. So this platform as such as a satellite should have this, and that is where we add value in terms of providing smartness on the satellite by providing edge compute, etc. And other aspect is when you have to maintain this relatively position and other things, you need to have efficiently use your fuel. You don't have to do it every now and then you need to have a margin for it. So how to maintain the satellite for the life period, that is also a big challenge when you put a LEO satellite to maintain for more than 4 years, 5 years, yet having the fuel capacity is you have to optimally plan. So and also have redundancies as well. So once how you if for some reason you are not able to communicate or one of the satellites just goes off. So these are the challenges where we add value onto that. And most important, but not the least, is the security. When you are doing all this, we are all used to firewalls and many other things, hacking and many things which comes up in the internet domain. So how are you going to protect these assets in space, or even when you are communicating through this as a point to point? So this is a major challenge. So this is where we as a SAT-OS, as a protocol level, we have multi-layer security added to our satellite platforms, protect these satellite assets so that there is no malicious attack or something like that on your space. So this is the other aspect which we add value. And apart from communication, there's also in the mesh network, when we are talking about, there is also huge use case in Earth observation as well. So when we do imaging, or when you try to capture images, so one satellite for some reason couldn't image, or maybe the imaging conditions were not good. So passing on this information in real time to the next satellite, either coming or maybe the adjacent satellite in the different orbit, and then asking it to take a image is one of the use cases which we do in the EO domain in the mesh network. And there's also one more use case where we try to add when we are talking about mesh network, I'm also meaning inter-satellite communication is already set. That is by default, it's already there. So a tip and Q kind of a configuration, like where you see certain area of interest, and there's something which is of area of interest, or some unusual thing has happened on that, and then you want to communicate to the next satellite coming, or maybe you want to have one more satellite in a complementary sensor to just take that image of that region. So this is also comes under mesh network in the EO domain. So these are some of the areas which XDLINX is working, and then we build all these in our platform and provide as a service. Thank you.
Thank you very much. So I'm not sure if there's still some time. Yeah, unfortunately, our chair has not arrived. So I take over maybe to find out if there are questions on this topic, because it's I think looking into the sessions, there's a certain complexity here, yeah, and you have to try to get into it. And I think us three, we made here a decent job, yeah, and I hope you enjoyed it. But if there are any questions, please raise your hands, and we try to answer.
Hello, good afternoon. I'm Anupam Tiwari, and a small question. Whatever you have discussed from a architecture point of view, the solutions you have discussed in your slides, and Dr. Pramod had mentioned about security. So how will this all be impacted in case from a futuristic, maybe 5-7 years down the lane, adversary has already done it with respect to the quantum communication. So in case we set up quantum communication or we look forward to it, how will this be affected?
Yeah, so interesting question, for sure. I think one aspect of that is post-quantum cryptography. So we have already started evolving some of our algorithms to support that as a mode for securing access to the system itself. If you want to get a little bit wild with our ideas, if you look at some of the work that is being done at TU Delft, for instance, they are actually trying to develop quantum networks. How that is going to evolve, I have no idea, because if the data can magically appear in another place, cool. Would you really need a sophisticated system to control that data flow? I think that is going to remain true. The other aspect of most of quantum computing right now is it is still incredibly expensive. So that 5 to 10 year time frame, I think the earliest that we are going to see viable large scale quantum system in use in communications, even if it is for key distribution, for instance, just for cryptography, I don't foresee that happening before 2035. I know there are some trials in Europe that are working on exactly that right now. They expect to launch later this year, or rather later in a couple of years. It's still early days. I know it is going to happen 100%, well, 99%. Yeah. But it is going to evolve in unpredictable ways, in my opinion.
I maybe add.
I'll take this question.
Oh, sorry.
So thanks. So thanks for the question, sir. Coming to the quantum cryptography side, I think a lot of developments are happening in QKD domain as such. Probably in the next coming 1 year, we have signed up with one company for QKD payload. So probably we'll have one tech demo satellite which will be next year, which we'll use it for QKD purposes, and we use that for key distribution, and then do the following up with the encryption of standard AES and other things. So it has many advantages. Instantaneous key distribution is what we are trying to, and dynamically change this and then see the communication happens securely. So this, as a tech demo, we are planning to do it in the next year or so. Thank you.
Yes, that's what we see also. There's a lot of demonstrations going on in regards of quantum key distribution via satellite. But it's a long way to go, because doing a demonstration, that doesn't mean you can deliver hundreds, thousands of keys, yeah? Because at the end of the day, we are shifting here terabytes. So you can think about how many keys you need, and how many keys you need to exchange and save and storage. But definitely quantum and quantum key distribution is a big topic, and there's a lot of money going into that. But what I wanted to add is quantum computing, edge processing in satellites, of course, makes in principle most sense if you're having the capability of mesh architecture. That means you utilize data centers in space. Yeah, there's a lot of ideas. Can I have something which is not connected to my internet, my autonet, for example, Rivada? Yeah, they are saying rooftop to rooftop, gateway less, an independent network. So this architecture is in principle the basis for it. Yeah, that's on that side. Any more questions? Oh, yes, 2. That's great. 4, 3. Yeah, okay.
So with the rising interest in human commercial space exploration and possible tourism, when can we expect private satellite companies to enter into this field and provide, let's say, mapping of other moons and commercially not moons and planets for like future space mining missions and human space exploration missions? When can we expect satellite companies, private satellite companies, to either partner with spacefaring companies or independently explore the potential of space mining, etc.?
Good question, because this comes back to the relay satellites. And sometimes you need relay satellites. For example, even if you are operating on the backside of the moon, you cannot transmit directly. You have to go in principle mesh. And if you go further, maybe again, yeah? And, but I don't have an answer, honestly. There had been some initiatives with ESA. There are some ideas to build constellations around the moon, which can maybe even extend to the Mars, but yeah.
Yeah, so there are a couple of companies that are starting to make inroads in that area. There's one that is launching a commercial space station that should be going up in a couple of years. I know they have collaboration with Airbus and Mitsubishi and a few others, so it's serious. The ISS is going to be decommissioned in 2030, most likely, or 2035. So by that time, we'll have a commercial alternative available. That's the way NASA and ESA are starting to fund some of their investments. At the same time, there is increasing amount of investment now from a couple of startups towards lunar missions. And when I say lunar missions, they don't necessarily intend to land on the moon. Well, some do. It is for establishing, like Alex mentioned, that cislunar presence, so that there is a relay capability. More on that once they establish the lunar capability. The next step becomes you do it on Mars. So it's happening. It is seeing a lot of investment. The fruits of that, I think, are going to start appearing in, I'd say, 5 to 10 years. Mining of asteroids is, I think, it is a pretty real thing. It is going to start happening faster than we expect.
I think, to answer your question straight, as a private company, to invest in such large interplanetary exploration and asteroid mining and other things, as such, I don't see commercial viability for private players to really, people with very deep pockets may try and may invest in some research and such kind of thing. But by and large, for a private company, it is not really viable for making such a investment. Let me be honest with you.
Thank you. Mr. Rajiv had a question?
Yeah.
Okay.
Do you want to go? Thank you, sir. Sir, so the panel talked about building software-defined architecture and mesh nets for satellites, but the operation and the data centers will be taken care by the companies and startups on Earth. So I was wondering if we could actually load physical servers in space and conduct all of the operations in space. So are there companies or startups that work on actually building like servers outside space, or carrying out, having GPUs and TPUs in space and doing all of the operations? So
Yeah. Microsoft already has put compute on the ISS. If you look at a lot of the new software-defined satellites that are going up, all of them have a sizable amount of compute on them. Because a lot of their beamforming, beam shaping, decisioning happens on the satellite. It has to happen on the payload. So it is starting. Whether you can control your entire mesh network from a satellite, technically it is possible. There's nothing preventing you from doing it. There is no reason for a commercial operator to do it, because that is the most expensive compute you can ever buy. But for defense, it is viable.
Yes, there are definitely startups and undertakings considering that, and even having business plans on that, keeping data away from Earth. Yeah, whatever happens on Earth, you don't want to have it too close to Earth. But I think one of the challenges we have to see that GPUs, yeah, usually they need a lot of power. So this is something which need to be handled. Power efficiency, the heat dissipation, and so on. These are things which need to be handled much more than in space than on Earth. Yeah, on Earth we neglected that until a few years, but now we also have the problem here. I only want to give an example. In Singapore, for example, you cannot build any more data centers. Yeah, in other cities they also said, okay, no more data centers, because the heat generated in the cities through data centers, the power consumption in the cities through data centers is a challenge. Of course, we have evolution on the processing power, on the processor generations, so data centers still growing, but this is of course something you have to be even more managed in space. Okay, Chief? Oh, sorry. Yeah.
Thank you.
Short question, sir. This question is for Mr. Anish. I'm Rajiv Gambhir from SIA-INDIA. Anish, I saw your solution. I was trying to understand it. Question comes to mind is, what's your market? Is it the satellite operators or is it the user segment? Who pays for that? Part two is, you've come all the way to India. You wish to engage with the Indian space ecosystem. What are the kind of segments that interest you for engaging in the Indian ecosystem? Thank you.
Thanks. A question I was hoping someone would ask. So we have found interest from both the satellite operators as well as end users of hybrid satellite capacity. And the way I define end users of hybrid satellite capacity, it is governments, but also some value-added solution providers. So think about Marlinks and the Speedcasts of the world. If you are a consumer of capacity from a number of different types of satellites, and you are a valuable enough consumer of it, you can get access to APIs directly into their systems, and you can have more control over how your connectivity becomes available. And that control is valuable. For government agencies, it's obvious they need a hyper-resilient system that combines capacity from both their own systems, creating this sensor shooter pairs, from detection of a launch to a tactical response. And then in the operator world, it is an evolving industry. There are some operators that are focusing specifically on relatively large NGSO systems, so they are meshed by nature by having ISLs. There are others that have gotten into a situation where, because of acquisitions, they have diverse types of assets. And as a result, they have ended up with a semi-mesh network, is what I call them, because they're not entirely meshed. You can't route wherever you like, but there is a notion of intent fitting, where you can start selling services where you can choose the right kind of satellite to deliver parts of service to a particular customer. So your ultra low latency service goes through LEO or MEO, which tend to be more expensive to deliver. And your highly resilient service that needs to be available most of the day goes through a geosatellite, because, well, the cloud cover really doesn't impact C-band, for instance.
Thank you. I think if there are no more questions, we will finish the session here from my side. Please give me an applause for the panelists, me and the panelists, of course. Make it clear. And then I hand over to the MC.
Thank you so much, sir, for providing such valuable insights during the discussion. Well, now, ladies and gentlemen, with this insightful panel discussion that we are closing, we now have the opportunity to express our gratitude to our esteemed panel members. Well, I would like to invite Mr. Rajiv Gambhir, Deputy Director General, SIA-INDIA, to please come forward and felicitate our esteemed panel members. I request Mr. Alexander Jeuck, Senior Advisor, Novaspace, to please come forward. I request Mr. Pramod Kumar, Senior Vice President, XDLINX Lab, to please come forward and receive their felicitation award. I request Mr. Ashesh Mishra, Head of Client Solution, Aalyria Technologies, to please come forward. I request you all to please come forward to take a group photograph. And a huge round of applause for our audience for being so patient today. Thank you so much. Sir.